We're going to do lesson 19. Normally I wouldn't call this a new lesson, but because ultimately I'm going to put this on the internet later on, it might be good just to break these into separate lessons. We're going to do what I wanted to finish up with, which is the start of the day we start with mitosis, the end of the day we end with meiosis. We are going to describe the importance and process of meiosis. Now we're not going to go into huge amounts of detail. Like I've been looking at like some of the online videos and they go into really lots of detail. We're going to just keep it nice and simple. Let's just reflect briefly about this morning, what we did. And I've also made some nice little videos which should help. We said mitosis first. So we've got mitosis versus meiosis. Mitosis is all about repair and growth. It's how the body makes new cells. But what's important about these new cells that get made, and yeah, Brendan, by the way, here's your answer. We're starting off with the parent cell, which is just one, and we finish up with the daughter cells, which are two. There are two cells at the end, and they both came from the same original cell. So that cell gets destroyed as it makes those new cells. What's important here is they are exact copies of each other, or clones. And I'm going to refer to that a lot when I do talk about meiosis. I want you to understand that they were the exact same cell. This one had 46 chromosomes. Those 46 chromosomes all got copied. And then one copy goes here and one copy goes here. They are exactly the same. If I was to look at this cell and this cell at the end, well, I can't because it's destroyed, but if I was to look at them, they would be the same. And these two are the same. They're identical. The reason they're identical is because ultimately, so that means in theory, every single skin cell in your body is the same cell. It has the same DNA, it has the same shape, it's exactly the same. And that makes sense. You don't want some skin cells to be one type and some skin cells to have a different DNA, because then those DNA might get confused and you might lead to issues. You want everything to be the same. Well, that's true, and how it works is we copy the DNA. We copy the DNA by just, slotting in another side, and each pair matches with another pair. We end up with 2 strands of DNA. Now, I've made this look a bit better. I spent some time on this. I'm actually pretty happy with this here. So how does this work? Grab a look at this.
They're different sizes, eh? They're different sizes, right? Or
yeah, so that's what I wanted to do. I wanted them to be different sizes. The reason for that is because these two are the same length. And these two are the same length. And the reason that they're the same length is because they are diploids. They are pairs. They come in a group of 2. So each of these has its own little pair. What happens is that each of those then gets copied, and you end up with all of these copies. Once you've got all these copies, what you can then do is you can then split those copies. And because I drew this last time, now I've got actual better things. You would split those copies into 2 different cells. One cell gets let's just paint, will get half, and the other cell will get half. And what I want you to see is, notice I did this slight change of color here because ultimately, if you think about it, this is chromosome 1, this is chromosome 2, this is chromosome 46. Each cell will get a copy of chromosome 1. Each cell will get a copy of chromosome 2. Each cell will get a copy of chromosome 3, and so on. So if you look, each of them is getting one of the sides. either the left side or the right side. And then because both of those sides are exactly the same, that's okay. You end up with 2 new cells, okay? Both of those new cells have all of the DNA. Both of them have 46 chromatids or 46 chromosomes. And therefore, it's everything standing. So what's the difference between mitosis and meiosis? Well, meiosis is all about is getting away from that idea of chromosomes. This is new stuff. Mitosis is the act of taking one cell and turning it into 4 cells. So instead of one cell becoming 2 cells, this is one cell becoming 4 cells. But what's important is meiosis is the process of creating sex cells or gametes, like sperm cells or egg cells. Oh no, sorry, this is the important part. Each of these cells has a different genetic code. Rather than this one, where they're the same, this one, they are different. So maybe one's got like, maybe one's like, crosses on it, maybe one's got dots on it, whatever. They're each different. Now, meiosis is the process of creating sex cells or gametes, like sperm and egg cells. Now, I talked about this word before, but I'm using it again just so you can get familiar with it. The word gamete is what we refer to either sex or egg cells. The reason we have them is because we want to just have a word that we can use for anything. This process isn't necessary. In fact, some organisms reproduce with just using cloning, using mitosis. Sea stars and some mushrooms are an example of that. What they do is they just go, right, I'm going to copy myself, and they makes a brand new copy of itself, and then that other copy just goes on. And so you might have a population of sea stars or starfish that are all clones of each other because, whatever. So why do we bother going through sexual reproduction if we could just clone ourselves? The difference is the advantage of sexual reproduction is there is more genetic diversity. And that means there are other reasons why it's a good thing to have genetic, which you can explore if you do year 11 biology. But another reason is it's good adaptation to change. It's really good for evolution to be able to change your DNA. If you just had the same, like we had the same exact DNA as our ancestors, then we might not have been able to walk on 2 legs. We may not have, been able to be hairless and stuff like that. So, it means for adaptation. There are some other disadvantages of it though, but we'll talk about that later on. Down the bottom, yeah.
For the first point that says mitosis is the act of taking one cell and turning it into 4 cells.
That should be meiosis, yeah. Is that what was that your point? Because you are completely right there. That was a typo on my half here. Meiosis is the act of taking one cell turning it into 2. Yeah, this one here is correct though. Down the bottom is the stages of meiosis. So how we go from 1 cell into 4 cells is what we do is we go through we go through 2 divisions. So we go 1 to 2, go from 1 to 2, and then from 2 to 4. And if you look down the bottom here, you can see this. Now again, luckily you don't have to memorize each of these steps. All I wanted to show you guys with this picture is just to show, hey, look, this section here looks a lot like mitosis. We're just copying the cells, we're splitting them up into 2 groups. But then each of those 2 gets split into 4. And then that leads us to then have, this is the second division here. Oh, well, the second division, and that second division then makes 4 cells, each with less of the chromosomes. And I'm going to talk about how much more less. This has got a lot of text on the slide. I'm happy for you guys to come back to the slide later on. But can I move on?
Yeah. Sorry, I don't know if anyone else has finished, but I finished.
Okay, cool. That's right, Alethea. I'll take your word for it. Ooh, screen went black.
So you're recording these sessions, right?
Yeah. So I will put them up on YouTube and the internet later on, but it's going to take it won't happen straight away. It'll probably go online at about 4:35. So if you want to check back then, you can probably see it. But yeah, you can. And the advantage for you guys, which is one of the rare things that makes this better, is that when you guys, because we're going to have to do a test on this, when we do the test on this, you guys can just go back over all of this stuff as revision, all of these videos. Let's talk about some special features of meiosis. So the meiosis includes one special feature. Before a cell splits in meiosis, the DNA allows genes to cross over. Some genes from one strand of the DNA swap with genes of the same pair. Okay, this leads to more genetic differences because ultimately, first thing you're doing is you're just mixing things up a little bit. So in the picture on the right, can I get everyone to look over here for a sec? I've got one side and the other side. These are two, this would be like chromatid 1, this is chromatid 2. You know, it's completely different chromosomes. What we're going to do is we're going to take some of chromatid 1, we're going to move it over to chromatid 2. We're going to take some of chromatid 2 and we're going to move it over to chromatid 1. We're just going to swap some of the genes around. That'd be like, essentially that'd be like saying in your body, like in your chromosomes, you're taking, because remember, these chromosomes, the pairs are because one comes from your mum and one comes from your dad. So what you're doing is you're taking some of your mum's chromosomes and you're mixing around with some of your dad's chromosomes. But I don't want to get into too much detail on that. I'm afraid that I might confuse you. The idea is, all you need to know for this bit is you just do a little bit of swapping at the start. It's like what you would do is you would take your deck of cards and you would just do a little bit of a shuffle at the start. Not a big shuffle, a little bit of a shuffle. You're taking half the deck and you're like you're taking half the deck of cards and you're you're shuffling them up with the other half. So yeah, that's all we're doing. We're just, just a quick little shuffle. This is important because we're going to talk about, it makes more genetic differences. We're going to talk about why genetic differences are important later on. Now, what's the next step in this? So we've swapped some of our DNA around. Okay, yeah, so what? Let's have a look at what difference this makes. Okay. Here are all, this is one cell at the moment. And here are all 46 chromosomes. Yeah. Here's the first one. Second one. Third one. Fourth one. What I've done to try and make things a little bit clear is I've actually made each of these a different color. So you'll notice that 1 and 2, these guys are pairs. Can you see that one's dark blue and one's light blue? Is that clear enough for you guys to see? Can I get a yes or something?
Yeah.
Okay, cool.
Yeah.
So 5 and 6, those two are pairs. One's dark blue, one's light blue. Down here, we've got the sex chromosomes. So here is 45, and 46. So this could be an X chromosome and this could be a Y chromosome or whatever. It doesn't really matter too much. Okay. The first thing we're going to do is, just like before, each chromosome makes an exact copy. Okay. So here you've got 1, 1, 2, 2. These are still pairs. 3, 3, 4, 4, so on and so forth. X, X, Y, Y, whatever. Doesn't matter. But we've got, or this would be, I suppose, 45, 45, 46, 46. So we've got, each of these is now made a copy. This is just like mitosis so far, okay? We've done a little bit of a shuffle at the start, but now what we're going to do is, now we're going to take our deck of cards and we're going to cut them. We're going to move it like this. Okay, now this is now undergone cytokinesis. Okay, just like before, each chromosome makes an identical copy. The cell undergoes cytokinesis and splits into, that should be an S. Yep.
Do we have to draw all those?
No, Lethe, I'm not horrible. I just want you to mostly get this bit here. What I might get you to do at the end might be a quick little, not this, but like a small little picture, which I'll show you at the end. I'm just trying to get you guys to see this so you can understand what's going on.
Okay.
Grail, is this the same thing that with the roach and stuff, this chromosome thing?
Which, yeah, exactly. So first
So you're telling me there's 23 pairs of ropes, right?
Yep.
Okay. I only understand it if you talk about ropes. That's like the way I'll understand it.
All right. Well, we'll just do that. Well, Brendan, you know what? Because I like you, we'll just say what's happening here. There are 23 pairs of rope, right? One of them's red, and what we've done is we made a copy of each of those pairs of rope. So now we actually have 92 strings of rope. In each of those strings, 4 of them are the same length. Okay? This one, this one, this one, and this one are all of the same length because these 2 are pairs and these 2 are copies of those pairs. Now, if you don't get, what we're going to do now is, of course, and this is going to make 2 cells. Here's cell 1 and here's cell 2. Now at this point here, whoa, slow down. I'm not up to that bit yet. Here's cell 2. Now at this point here, right, these cells are the same, sort of. Start ignoring crossover, these cells are the same because it's exactly like mitosis. Each of them has a copy of chromosome 1, right? Each of them has a copy of chromosome 2. Each of them has a copy of chromosome 13, whatever, you know, you get the point. Each of them has one copy of the other one. Where it becomes interesting is then I'm now going to split this again. Okay, I'm going to split it like this. Now I have 4 cells. A, B, C, and D. So what I've done is I've taken my deck of cards, I've cut them in half, and then I've cut them in half again. What we've got what we've got here is what's interesting in this one is this has only got 20. Well, if this had 46 at the start, then this has got 23 and this has got 23 because half of 46 is 23. This has got 23. And this has got 23. But what makes this difficult is now they're no longer exactly the same. Let's have a look here. For example, here we've got chromosome 1, right? Over here we've got chromosome 1, but these two don't have chromosome 1. This one has a chromosome 2. This one has a chromosome 2, but neither of these two have a chromosome 2. Maybe this one's got chromosome 5. And this one's got a chromosome 3 and a chromosome 4. But this one's got a chromosome 5 or whatever, you know? Actually, no, that's not how it would work. I got that wrong. This one, it has to have either the first one or the second one. So maybe this one's got chromosome 4 and this one's got chromosome 3. Maybe this one's got chromosome 6, but this one's got chromosome 5. Whatever. My point is, the cell undergoes cytokinesis again, splitting into 4 cells, each with 23 chromosomes or 23 chromatids. They don't have pairs. These cells are haploids, meaning no pairs. Normally, 1 would be paired with 2, but now 2 is in a completely different cell. 3 would be with 4, but 3 and 4 are in different cells. 5 would be with 6, but now 5 and 6 are in completely different cells. Each of these is different. None of these are the same. They all have chromosomes. Not even these two. So not even these two are the same. Because this one might have 1, 3, and 5, whereas this one has 2, 4, 6. This one has 1, 3, 6. So they make completely different cells. And this is important. The reason why this is important is because, and I'm going to talk about this here, the reason this is important is because it leads to diversity. This is why there is so much diversity within the human population, even between brothers and sisters. This is the example that we usually give here. You take a brother and a sister, right? They both had DNA come from their parents. But we've seen that one cell can divide into 4 completely different cells. There's actually 8,388,608 possible different ways to split those cells. Split that DNA. And that's ignoring the fact that we've already got a random shuffle at the start. That's why it's just so diverse. To answer the thing that I asked you to do before, Alethea said, do I have to draw something? What I think might be good to draw is just to start off, just to go with this idea of drawing pictures. We're going to draw pictures. We're going to draw a bunch of lines. We're going to draw a bunch of crosses. We're going to go to 2 cells, each of the 2 of those, each with a bunch of lines. And then that's going to go to a run out of space. Of course I have. That's all I want you to draw, Alethea, just to summarize what you did. First, we make
Okay. I was just saying okay. Yeah.
Okay. So first what we did, and I might write this, first we go for a copy, then we go for a split, and then we go for another split. We split the split. You'll also notice is that we always end up with even numbers. We split to make 2, we split to make 4. We don't split and get 3 or 6.
What happens if there is a 3?
If there is a what?
Like, what happens if it's not an even number?
Well, that's one of the things that I would like to add, and this is a bit of an extra thing. You will always get 2 cells and 4 cells. But I just wanted to quickly say this. Imagine that you have, this cell has 4, like first we've got, you know, 1 cell. We've got 1 cell which, you know, splits into 2 cells, each with 46 chromosomes. And then those chromatids, and then they split to make 23 and 23. But what if one of those accidentally splits and makes 22 and 24? Could that happen? That could happen. That has happened. And that's exactly what we were talking about before. Remember when we said, oh, there is a situation, sometimes like, for example, Down syndrome, where you have more Down syndrome, which is when you have trisomy, which means you have 1 extra chromosome. How do you get 1 extra chromosome? This is how you get 1 extra chromosome. When it splits, but instead of splitting equally, it splits unequally. One of the cells ends up with too many chromosomes. And your body makes mistakes like that all the time. I mean, there are probably, you know, there are probably egg or sperm cells in you that have already done this. But the chance of you, you know, having a child with that issue, you know, is low, but it does happen. So that was a bit of a side. You don't need to copy this part of the top down. I just wanted to show you guys, hey, yeah, it can stuff up. It can split wrong. So this sort of answers the question why, you know, you might have 2 children, or, you know, your brothers and sisters might be similar to you because you both come from the same genetics. You both come from the same DNA. But because that DNA has been shuffled differently, it's pretty much impossible for 2 babies, you know, born at separate times to be clones of each other. However, there is a way that you can get 2 babies that are clones of each other, and it happens quite regularly. Do you guys know what it's called when you have 2 babies that look exactly the same?
Twins.
Identical twins.
Identical twins. This is the last slide, so we're all good here.
Do we write it or no?
Yeah, I think I want you to write this because it's important. Plus, I think it's also useful because it's like the amount of questions that people get wrong about twins, and also if you have twins, because, you know, it'll be a good idea. I think twins are about pretty common. Like, I think they're about like 2%, 1% of the population. So you could end up having twins if you have children.
That's crazy because one could be a girl and the other could be a boy.
Yeah, and that actually happened. One of my, I'll talk about that in a sec. One of our friends had twins, and there was a boy twin and a girl twin. It was funny because they didn't look at all the same, but yeah.
Yeah.
So have you seen the interracial twins?
Yeah, well, that can happen too, because again, the genetics are different. It can happen. It's weird, but yeah. So there are 2 types of twins, right? Identical twins occur when one fertilized egg or a zygote splits into 2 cells. So normally what would happen is you get 1 cell, splits into 2 cells, splits into 4 cells, splits into, you know, 8 cells, so on and so forth. The only difference here is that 1 cell splits into 2 cells, but then those cells just go off and do their own thing. One of them goes to make, you know, 1 baby, and one of them goes off and makes another baby, and that's how you end up with identical twins. The trick here is, though, is that those cells make new organisms with the same DNA. Think about it. There was only ever 1 egg and 1 sperm. So there's one type of DNA. So here's the question for you. Could you, with this one on the exam on the left, could you have identical twins and one of them be a boy and one of them be a girl?
Wait, what?
Would they be identical though?
Well, that's the
I
question. Could you have identical twins with one being a boy and the other one being a girl?
No.
No.
Wait,
Because
You can.
the
You
only
can.
way.
No, you can't.
You can.
No, you
You
can't.
can't.
I've seen it happen.
Because they have to have the same DNA.
Then
And,
yeah, DNA.
and if one is a boy,
Oh, identical to. Oh, okay. Never
if
mind.
one is a boy and the other is a girl, then they're not
Yeah.
identical. Now you
Like, I
can't-
thought you meant twins.
well, these are twins.
Yeah, but he was asking if one was a boy and one was a girl, would they
Yeah.
have the same?
Oh, okay. I didn't hear that part. I just said, oh, is it possible to have a boy and a girl as twins? I was just like, yeah.
Now
Oops.
you can have a boy and a girl that are twins. Those would be called fraternal twins. Now, what a fraternal twin or a different twin, doesn't matter really, is when two eggs are fertilized by two different sperm. These make two babies with different DNA. So you end up with one, because this is 1, 2. These are two different types of DNA. This is 3, 4. These are two different DNA. And so these end up with a boy and a girl. Now, in this case, you could have a boy twin and a girl twin. You could have two girls. You could have two boys. That's possible as well. It doesn't matter. You just, and usually they won't look they will look similar because they're brother and sister, but they won't look identical. Now, you can have, there are other types of twins. I've only gone through the two major ones. There are other types of twins. I only learned about these ones recently. For example, you could have one egg that gets split into two, and then those two eggs get fertilized by different sperm. So then both of them have the same copy of the mother's DNA, but they both end up with different copies of the father's DNA. So they're like half identical, but yeah, we're not going to.
It's 3 or 7, sir. It's
Yeah,
3
yeah,
or
that's right.
7.
I'm pretty much done. That's it. So,
Okay.
but that's the point, is that, yeah, those, and yeah, of course, we know we've got identical twins stuff, because, you know, they're, I just thought I'd throw that up there. So they're both pretty much clones of each other. There will be some differences in the way, in how they think, and obviously, but yeah, a lot of their DNA are very, very, very similar. Ladies and gents, that's it for the lesson. What I'm going to do is I'm also going to get you, but I'm going to give you longer for this one. I'm also going to get you to do the meiosis on, the meiosis questions on meiosis, which is on the style as well. So that's also going to be something for homework. But again, with the mitosis meiosis, I've cut out a bunch of the questions to make it a lot easier. There's only like, I think, 11 easy questions to do with the meiosis and style. So I want you guys to get onto that and give it a try during the week. And we'll talk about, next week, we're going to talk a little bit more about genetics, but specifically about what happens when, you know, we're going to talk about specifically how different traits can exist, and, you know, how come if my mum's got blue eyes and my dad's got brown eyes, why do I end up with brown eyes? That's going to be one of the ones we might be talking about. Anyway,
Because
guys,
the dad has, you know, more stuff.
yeah. All right, guys,
You know.
that's all for me. Have a great
Bye.
weekend. I will